In this video, we are going to look at the probabilities of dependent and independent events. Let's start with an easy example and one that you might be familiar with. If a couple would like 2 children, then they have a few options. They could either have a boy and a girl, or 2 boys or 2 girls, or a girl and a boy. And we can show all these combinations in a tree diagram. So for the first child, they could either get a girl or they could get a boy. Each of these options is a 1 in 2 chance because there are 2 options, and the chance of getting a girl is 1 out of the 2 options, and the chance of getting a boy is 1 out of 2 options. After having a girl as their first child, they could also have a girl as the second child. Because there are also still just 2 options, having a girl after the first girl is also a 1 in 2 chance. But so is having a boy, because there are still just 2 options, having either a girl or a boy. The same is true for when the first child is a boy. The second child could either be a girl or a boy. And just like in the branch above, having a girl is a 1 in 2 chance, and having a boy is a 1 in 2 chance as well. So these are all individual events. Every time we have a branch, it basically indicates the mom having a child, and in that specific incidence, in that pregnancy, there's a chance of either having a boy or having a girl. Here as well, this is one event here, and in this event there are only 2 options, and having a girl is 1 in 2 options, a 1 in 2 chance, and having a boy is a 1 in 2 chance. The outcomes, on the other hand, indicates the consecutive events. And with consecutive, we means the one after the other. So if you have a girl and then a girl again, that is an outcomes, or that's the consecutive events. So we could either have 2 girls, first a girl and then a boy, first a boy and then a girl, or 2 boys. There are 4 options here, so it means that having 2 girls is a 1 in 4 chance, having a girl and then a boy is a 1 in 4 chance, having a boy and then a girl is a 1 in 4 chance, and having 2 boys is a 1 in 4 chance. If, for example, you were asked what is the chance of having a girl and boy, and that could be in any order, that would be a 2 in 4 chance, or half a chance, if you simplify that fraction. Our options every time remain either a boy or a girl, and this does not change from child 1 to child 2. Therefore, these are called independent events. Let's look at another example of independent events. So I'm sure you all know the game rock, paper, scissors. So in this case, we have 3 options, either rock or paper or scissors. So player 1 has the option of rock, papers, or scissors, but they are not sure what player 2 would play, because player 2 would have those same options. If player 1 chose rock as their option, then it means that player 2 could also choose rock, or paper, or scissors. If player 1 chose paper, then player 2 still has the option of rock, paper, or scissors. And the same for if player 1 chooses scissors, it could be rock, paper, or scissors. The option every time of choosing a rock, paper, or scissors is a 1 in 3 chance. And this is the case for every event because every time there are only 3 options. So I'm going to write a 1 in 3 chance here on each of the branches, showing that each of these events happening have a 1 in 3 chance. But let's now consider the consecutive events. Having 2 rocks would be one of my options. So this is basically a draw. Then having rock and paper is my second option. And here I can ask you which player wins, and if you know the game of rock, paper, scissors, you know that paper rocks wraps around a rock, therefore player 2 wins. My third option is player 1 has rock and player 2 has scissors, meaning that in this case, player 1 would win. And as you can see from this first 3 sets of outcomes, we can now predict what the chances are of each player winning. Would it be the same or would it not be the same? Let's have a look. So in the second instance, we have player 1 playing paper every time, and player 2 can have paper and rock, or paper and paper, or paper and scissors. And let's see who wins every time. By now you should know that paper wins over rock, so that means player 1 wins there. 2 papers would be a draw, so nobody wins. And paper and scissors means that player 2 wins. Let's go on to the last one. Here we have scissors for player 1 every time. And for player 2, we have rock, paper, and scissors. So scissors and rock means that rock will win, so that is player 2. Scissors and paper means that player 1 will win because scissors cut paper. And scissors means that it is a draw. Now, hopefully you see that there are 9 outcomes in total. So each of these outcomes would be a 1 in 9 chance. So it's always a good idea to fill this in on your tree diagram so that when you are asked questions about the tree, you can answer these questions. If, for example, you are asked, what is the probability of it being a draw, you can go and look for the word draw in each of the 9 options, and you will see that there are 3 of them out of the 9, meaning there's a 3 in 9 chance or a 1/3 chance of there being a draw. The same for player 1 is also a 3 in 9 chance, and the chances of player 2 winning is also a 3 in 9 chance. And remember to always simplify your fractions. Because I have 3 options every time, rock, paper, scissors, and these options do not change, these are also independent events. So let's consider dependent events. In this case, I'm going to work with 3 jelly beans, which is a fairly small number, but it's going to make things a little bit easier. So that means that I have a red jelly bean, a blue jelly bean, and a yellow jelly bean to start off with. Just like in the previous example, choosing either of these jelly beans would be a 1 in 3 chance. But if you like jelly beans as much as I do, you would eat the jelly bean after you've chosen it. So after you've chosen and eaten the red jelly bean, you now only have a blue and a yellow jelly bean left over. This means that choosing a blue one is a 1 in 2 chance and a yellow one is a 1 in 2 chance. And there is no red jelly bean because you've eaten it. If, however, you chose a blue jelly bean, you will now have a red jelly bean left over along with a yellow jelly bean. Because there are now only 2 jelly beans, choosing a red one is a 1 in 2 chance, and choosing a yellow one is a 1 in 2 chance. If the first jelly bean you chose was a yellow jelly bean, then it means that you only have a blue and a red jelly bean over. And choosing a blue one is a 1 in 2 chance because there's only a blue and a red, which are 2 options, and choosing a red one is a 1 in 2 chance. So let's go and have a look at the outcomes. You can either have a red and a blue, or you could have a red and a yellow jelly bean. You could also have a blue and a red, or a blue and a yellow jelly bean. And lastly, I could have a yellow and a blue, or a yellow and a red jelly bean. So drawing the tree diagram really just helps me to organize all my different outcomes. So the options after red is blue or yellow, so I write red, blue, red, yellow. The options after blue is red, yellow, so I write blue, red, blue, yellow. And the options after yellow is blue and red, therefore I write yellow, blue, and yellow, red. If you count these, you will see that there are 6 of them, meaning that choosing any one of these would be a 1 in 6 chance. Sometimes the tree diagram would be too big, and it would be simpler just to merely list all the different outcomes or the options. So I'm sure you've seen this question before, where there are 4 horses competing in a race. We can label them A, B, C, and D, and we would like to know the order in which the horses finish the race. So obviously one of the options would be A, B, C, D, but it could also be A, B, D, C. And maybe horse B wins the race. So then it's B, A, C, D, and maybe horse C wins the race, and it can become very confusing. So it's always a good idea to start with horse A winning the race, horse B winning the race, horse C winning the race, and finally horse D winning the race. And in each of these columns, write all the different combinations. So we already have A, B, C, D and A, B, D, C. So you will see in this case, I kept the first 2 letters the same. So now let's change it to AC and AC. So therefore I can have AC, BD and AC, DB. There's also the option of AD and AD, and then we can have BC or CB. And now I've done AB and AB, AC and AC, AD and AD, and remember I can't repeat A, so these are the only options for horse A winning the race. And we can see that there are 6 options. And that would be the same for horse B as well. So let's go and list it in the same manner we've done with A. So we will start with BA, BA. And I already have CD, therefore I will now have DC. Now I can have BC and BC. And after that I can have AD and DA. And lastly I can have BD and BD. Therefore, I can have AC and CA. And we also have 6 options here. And there we have all the different options. For horse A winning the race, there's 6 options. For horse B winning the race, there are 6 options. For horse C winning the race, there are 6 options. And for horse D winning the race, there are 6 options. Which means in total, there are 24 different outcomes or 24 different combinations. Now that you have listed all of them, it is so much easier to answer questions. So when you are asked what is the probability of horse A winning the race, you can see that this probability are all the ones listed in the A column. Therefore, it would be a 6 out of 24 chance. And remember that we can simplify this to a 1 in 4 chance. If we are asked what is the probability of horse B winning, it would be the same. Or we could be asked what is the chance of horse D not winning the race. And in this case, we will have to look at everything that does not include horse D winning, which will therefore be all of these options. And that is going to be 18 out of 24, which we can also simplify to 3/4. So having a list of possibilities really makes it so much easier for you to answer your question. So it does not always have to be a tree diagram. It can also be a neatly structured list like the one we've just made here.